Okay, this is 9-5 inscribed angles. Okay, let's start with warm-up. I think you remember doing this problem in the packet and also on the test. I think there's a typo here. I think this is measure of arc CBD, should be CBD. Okay, so that's 150 and measure of arc BD is 50, and you are supposed to find out measure of angle COD and measure of angle COB and measure of angle BAD. So we've done this and you can do this, right? So if this is 150 and this is 50, then this is 100. So if measure of arc is 100, central angle is 100, central angle here is 50, okay? And so COD is have to be the same as measure of arc, so 150. We've done this, and COB is this, that's 100. Now this one, you remember, this was the external angle of these two remote angles, and since this is both radius, these are isosceles, so these are 25 each. Okay, and if you look at this angle right here, it's the same thing, right? This is 100, so these remote two angles, sum should equal, and because this is isosceles, these are 50 each, right? And I wonder if you noticed some relationships here. Do you see any relationships that jump out at you? I don't know if you noticed that this angle to this angle is double, right? 50 to 100. And this angle to this angle is also double, 25 to 50. And that makes sense because this is external angle, and then these angles are isosceles, and the same here. This is called central angle, right? You remember we learned this. This is called the central angle. This angle right here is called inscribed angles. That's what this section is about. Okay, it's the angle that is made by an arc and on the circumference of the circle. That's inscribed angle. Okay. Right. So the objective here is solve problems and prove statements involving inscribed angles. Okay, and this packet has a lot of corollaries and theorems. All right, so here is the definition of inscribed angles. It's is an angle whose vertex is on a circle and whose sides contain chords of a circle. We say the angles at the right intercept the arc shown in color. So this angle intercepts this arc. Okay, that's just the term. So this is also inscribed angle, even though this is this arc is more than 180. It's still inscribed angle, and this is the arc intercepted by this angle. Okay, you can intercept a major arc or intercept a minor arc. Okay, so this is theorem 9-7. The measure of an inscribed angle is equal to half the measure of its intercepted arc. Now, the measure of intercepted arc is the same as measure of central angle. Okay, right? Because the measure of the arc is the same as measure of central angle, right? So that's what we saw here, right? The measure of arc, central angle, this angle is half of the central angle and half of the measure of arc. Okay, the theorem is written as half of the measure of arc. All right, so here is 3 situations, 3 different proofs. Okay, so ABC is intercepted in circle O, and measure of angle ABC is 1/2 of measure of arc AC. Case 1, the point O lies on the angle ABC. Case 2, point O lies inside ABC. Case 3, point O lies outside ABC. Okay, and here is the proof for case 1. So draw a radius OA and let measure of angle A, B, C, X. So this is X. measure 방법 A equal X, right? Isosceles triangle. Oh, I shouldn't say. You gotta, well, I already said it. It's because isosceles. Isosceles triangle. Okay? Now, these Y's you do now, okay? Measure 방법 A or C is 2X. measure 방법 AC is 2X. So measure 방법 ABC is 1/2 measure 방법 AC. Okay, now I want you to think about how to prove these two. Okay, so we just did this one. I want you to try how to prove these. Here is a hint. You can draw these radii and like that. Those are the auxiliary line for this one, this one. These are the auxiliary line for this one. So I want you to think about how to prove this, okay? Okay, next page. All right, example 1, find the value of x and y. This is homework. I think you can do this. Here is corollary 1. If two inscribed angles intercept the same arc, then angles are congruent. So this is the same arc. So measure angle 1 and measure angle 2 have to equal. So even like there's another angle over here, like really over here, like this, even though they don't look like they're the same angle, actually they are the same angle, okay? Because if you go like this, it falls in every situations. You can do the proofs that we did in the previous page. Okay, so if it's coming from the same arc, any inscribed angles are congruent. And because of that, if the arc is semicircle, then that's 180. So any inscribed angle from the diameter is always right angle. So if you have a circle and diameter and there is like a triangle drawn on it, it is right triangle, okay? And corollary 3. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. And I want you to think about this. I want you to think why this is. And we talk about this in class, okay? And what is the sum of the measure of the red and blue arcs? I think it's red and blue. Explain. I think this will help this. So do this for homework. Okay? So these are the process of thinking how to prove this corollary 3. Okay? And example 2, find the value of x and y. You can do this one. Okay? And I think this is the last theorem and then we have practice. Okay. So, study the diagram below from left to right. Point B moves along the circle closer and closer to point T. Finally, in diagram 4, point B has merged with T, and one side of angle T has become tangent. Okay, so here is our inscribed angle of arc AB, and as the arc AB gets bigger, because B is moving towards T, the inscribed angle is getting bigger. It's getting bigger, and finally, the B touched T, and then this become tangent. So these are all secant, right? Secant, because it touching two places. And here, this line become tangent. And apply theorem 9-7 to diagram 1, 2, and 3, these. And you have the measure of angle T is 1/2 of measure of arc AB. This measure is half of this. This measure is half of this. This measure is half of this. As you might expect, this equation applies to diagram 4. 2. Since we say that angle T intercepts measure of arc AB, in this case as well, diagram 4 suggests the theorem 9-8. Okay, and in exercise you will prove 3 cases of this theorem. Okay, so the measure of an angle formed by a chord and the tangent is the chord and the tangent. So measure of angle formed by a chord and tangent is this one. Okay, so it's go past beyond the circle, right? If I draw a bigger line, the angle we are talking about is this. That angle, the chord by the tangent, is the half the measure of intercepted arc, half the measure of arc AB here. Okay, whatever this measure of arc is, the half that is this. Okay, and if you extend this, I think there's some exercise later, but if the chord goes through a diameter and then you have a tangent, right? This is 180, right? And that's why this is 90. So tangent being 90 degrees to the diameter or the radius doesn't contradict with this theorem. It actually makes sense. Okay? For example, if PT is tangent to the circle and AT is a chord, then angle ATP intercepts arc AT, and measure of angle ATP is 1/2 of measure of arc AT. If this is 140, then this angle is 70. If this is 180, this angle is 90 degrees. Okay, so that's all the theorems you got here. Okay, let's just recap. So the first one is the inscribed angle is half of the central angle or the measure of arc. That's the first one. The second one is inscribed circles are congruent if they intercept the same arc. The third one, or the corollary 2, is the inscribed angle of the diameter or the semicircle. If the angle intercepts the semicircle, the angle is 90 degrees. This you use a lot on the different problems. And this one, this and this are supplementary, and this are supplementary. That's corollary 3. And so that's 4 things, and this is the 5th. Okay, so the chord and the tangent, this the theorem, this is the first, the 9-7, right? 9-7 also apply to the tangent. So theorem 9-8 is kind of extension of 9-7. Okay, all right. So why don't you do odds here? And most likely one of these is going to be a survey problem. An equilateral ABC is inscribed in tangent to the circle at A and C meet at D. What kind of figure is ABCD? So let's do this one together. Okay, so circle O and equilateral triangle A, B, C, and tangent to the circle at A and C meet at D. So tangent at A and tangent at C meet at D. What kind of figure is A, B, C, D? Okay, so, sorry, you couldn't see. All right, here we go. Tangent at A, tangent at C, meet at D. Okay, so this is 60 degrees, right? That means this is 60 degrees. This arc right here. No, actually, that's 120. Sorry, 120. Which makes sense because this cuts into the 3 pieces, and then the whole revolution is 360. This should be 120. This should be 120. This should be 120 because this is 60 and this is 60. Okay, what else do we know? We can use this, right? The tangent and the chord thing. Okay, so this is a chord, right? This is a chord, and that's a tangent. And measure of arc that is intercepted by this angle is 120. So this should be 60, right? Half of this should be 60. And this is a chord, and that's a tangent. And this measure of arc is 120. So this should be 60. right? And this is chord, right? And this is arc. So this angle right here should also be half of this, 120. So this is 60, right? So if this is 60 and this is 60 and this is a triangle, this should be 62. And this is already 60. This is together 120, 120. The two sets of opposite angles are congruent. So at least it's a parallelogram, right? And we also want to find out if it's rhombus. And these are same lengths, right? And since this is 60, 60, 60, this should be equilateral. So this should be the same. All four sides are the same. So this is rhombus. Okay. And that's it for today's video.